Yeah, good evening guys. So please type in the chat box. Am I audible? So please type in the chat box. Is the audio and video clear? Welcome Suman, Chinmay, Yogesh, Mudit, Vivek and all. Yes, all clear. Great. So we shall start the session today. So this is the fourth lecture in our series, and in this session we'll look at vapor power cycles, and of course this is the second part of the lecture. And in this lecture, basically before going to this lecture, in last class, let us have a quick revision on what we have discussed in last class. So in last class we have majorly seen diesel cycle, then we have seen comparison between Otto and diesel cycles, and we have seen for same amount of for same compression ratio, we have seen for same compression ratio plus same heat addition or same heat rejection, we have seen, or same heat rejection. In both these cases we found out, after doing a bit of thermodynamic analysis, we found out thermal efficiency of Otto is going to be more than thermal efficiency of diesel, correct? So this is what we have seen. Then after that we have seen for same P maximum, for same peak pressure, for same P max plus same heat addition or same heat rejection. We have understood these points technically in a well way, that we have observed thermal efficiency of diesel is going to be less than, greater than thermal efficiency of Otto, correct? So these are the things we have seen. Good evening all. Okay, so these are the things that we have seen in a broad sense, and also we have seen if cutoff tends to 1, then diesel cycle will actually tend to Otto cycle, correct? We have seen diesel cycle will actually tend to Otto cycle. So all these points, theoretically good points, we have understood. And also we have seen the lastly dual cycle actually. Okay, so we have also seen what is the process in dual cycle and how to analyze this particular dual cycle. Now one important thing here is, I just forgot to tell you, because in solving some problems actually in yesterday's class, we define something called mean effective pressure, which is actually important in engine calculations. Mean effective pressure. Similarly, something similar to this will also calculate in Rankine cycles, which is called mean temperature of heat addition. Okay, so first now let us see what is this mean effective pressure. Normally this P mean is actually the uniform hypothetical pressure acting on piston during the power stroke such that W net remains same actually here. Okay, so normally in case of expansion, or basically in case of power strokes, what happened, right from the beginning of the piston to the end of the piston, pressure on the piston keeps changing, because clearly the piston is moving, volume is changing, so pressure is also changing. But if you assume that there is some constant pressure throughout the expansion process, then what could be the value of that pressure? That is very much easy to calculate a lot of engine calculations when you go into details. Okay, so this is mathematically given as P mean times this swept volume is nothing but W net, which is PdV is what you have here. Okay, so this is cyclic integral PdV. So mean effective pressure, so P mean effective in general is equal to cyclic integral PdV divided by swept volume, which is also written as W net divided by Vs actually here. Okay, so this is actually the expression for P mean. Normally when I'm talking, of course in GATE syllabus we don't have this, but sometimes people, if they want, they can ask you, but this is the simple formula. Normally this calculation gives you a very easy maths for calculating indicated powers or big thermal powers, all these things. Okay, so anyway, right now I'm just putting it in the formula wise so that you can just refer it. Okay, so whenever they ask you P mean effective, just calculate the net work output of the cycle. How you can calculate net work output? Thermal efficiency into heat supplied. You know how to, you know formulas for Otto cycle and diesel cycle, and also you know how can you calculate QS. For QS in Otto cycle, QS is actually CV times T2 minus T1, and in case of diesel it is CP times T3 minus T2, correct? Sorry, in Otto also CV times T3 minus T2, in diesel CP into T3 minus T2, you can get W net by VS is what you will get. Okay, so this is actually a bit simple to analyze. So in also in addition to this, we have also seen the simple Rankine construction, Rankine cycle. So if you see this Rankine cycle, we have seen that basically you need a pump, you need a turbine, for continuous generation of power. Okay, so you need a turbine actually, and in this turbine we decided working fluid is vapor. Working fluid is clearly vapor, and working fluid is vapor, and clearly it's called vapor power cycle because this guy is responsible for the power generation. Okay, so this is in gate, just this formula, just keep that formula in mind. Okay, so in some cases if they ask you, till now I think it was never asked, but if they ask you it could be helpful. Okay, this time. Now let's see, you have a turbine here T. Now the job of this turbine is to produce continuous rotation of the shaft, and in yesterday's class I have shown you basically this will be coupled to a coupling, and it is coupled to a generator shaft so that power gets generated. Now clearly we have seen, if you have this turbine in general like this, then to continuously supply power to this is vapor, to continuously supply vapor to this turbine you should need a device which continuously generates vapor, and that's nothing but your boiler. Boiler is in the basic sense, but sometimes you also have the superheater in it. Okay, so it superheats. Superheater, this is what we have seen clearly in last class. Just I'm revising the things quickly. Okay, if you are in the last class you can easily understand these things, just a quick revision. Then to continuously feed water into this boiler we need a pump. So we have a pump actually, and we have seen from second law point of view, you cannot directly leave this to the atmosphere, rather you should decrease its pressure below much atmospheric pressure, which could give you a hope of and one more device which is like condenser. We have seen in last class also. So this gets connected here somewhere and you have a condenser. Okay, so you got a condenser. So this is how we are closing the cycle. So basically it goes in this direction and comes here, and finally it enters this pump. And if you see the process here, we are going to supply heat, and heat is going to be ejected from the system from the vapor in this device. Okay, and work is input into this, and work generally comes out. You can say W out actually comes out from this particular device. So this is the thermodynamic cycle that we have developed, and we have seen how this cycle got into picture and why we cannot leave this directly to the atmosphere, because in second law point of view, in calculation of thermal efficiencies, we need a condenser. So these are the things that I have discussed in the last class. Are you all clear till this points? If you are clear, now in today's class we will start from this diagram and we will try to analyze certain things. We will try to understand what happens to efficiencies, what happens to a lot of things actually. Okay, so is it clear to all of you till this point? This is till yesterday's class, that's it. Okay, nothing new taught today. Okay, yeah. Now yes, now let's see, if you draw it on a PV diagram, how this process actually looks like. That's what the main important thing. So constructing PV process, PV diagram for the working fluid in this cycle. And it's not like A standard cycles, because in case of A standard cycles, the gas is actually enclosed. Working fluid is enclosed in a piston cylinder, so mass of the system is fixed. But here, of course, the mass in the circuit is fixed, but all these devices are operating under steady state. Okay, and fluid goes into different devices here. There, in case of A standard cycles, you have only air. Okay, now let's see in this case, if you draw a PV diagram for this, someone is asking me how to get this PVTS, thoda confusion hai. So now you can see here P and V. Now clearly if this is pressure and if this is specific volume, now clearly in this point the fluid converts from vapor to liquid, and at this point fluid goes from liquid state to vapor state. So definitely there is happening certain phase change in this particular cycle. So first we consider the dome, vapor dome. Okay, you all know it. This line will be much steep as compared to this line. This line will be generally very flat, but this line is steep, means the liquidus line is actually very strong, very steeper actually. Now let's say we have two pressures. One is pressure at which the condenser is operating, so P condenser, and definitely the other is P boiler, the location where boiler is actually operating. P boiler. Then these devices are at constant pressures. Now if you see, let's say if the system is initially at this point 1, now from this condenser pressure to boiler pressure, we'll actually do the pressure rise with the help of a pump. The job of a pump is actually to convert mechanical energy into the stored energy in the fluid. So this pump is responsible for increasing the pressure from condenser pressure PC to boiler pressure, say PB for example. Okay, so the compression is, again, as I told you, isentropic compressions are always the best. So if you take isentropic compression, we have a compression like this, 1 to 2. Clear? Now in this boiler we will convert the liquid into vapor. So right now in the simple case, let's say there is no superheater, there is only boiler, then definitely this boiler, in this pressure, what's happened, the fluid will change its phase from liquid to vapor actually. So this is 0.3, this is actually a 0.3. So heat addition is taking place and liquid is getting converted to vapor at constant pressure, because during phase change and all, there is no change in pressure actually. Okay, then from 3, then let's say for example if this is 1, state 2, state 3 and also state 4. Okay, so from 3 is the exit of the boiler. From 3 to 4 there is an expansion in the turbine. So again, if you take isentropic expansion, the expansion appears something like this. Okay, so this is 3 to 4, this state is actually 4, so you have an isentropic expansion. Then again, condenser is a heat exchanger that's operating at constant pressure, so there is a heat rejection process. So this is your heat rejection. So 4 to 1 is actually heat rejection. Now if you clearly see, in this we are actually sending in work input, here you're actually getting out the work output, and here you're putting in heat, and your heat is getting ejected in this particular cycle. So this is how we can construct a PV. You have enough logics for each and everything. These two processes are isentropics, and clearly this heat addition and heat ejection are at constant pressure, and this part is also at constant temperature, because this 4 to 1 completely lies inside the dome. And normally if you take water as a pure substance, for pure substances, during phase change pressure and temperature are locked actually. Okay, so is this clear to all of you? Did you understand how we have generated this PV? If you know how we have generated this, then we will start TS. Okay, yes, is this clear to all of you? Did you understand how I have constructed this PV diagram, PV plot? Yes. Now let us convert this PV into TS, because whenever we are 1 to 2 volume decreases, correct, because compression, no? This 1 to 2 volume should decrease, no? Because it's compression actually. Compression in a pump. Clear? Look, this 1 to 2 is actually compression in a pump. So whenever you are trying to compress, of course this line won't be this much. Actually it looks like a vertical line because specific volume is almost constant. But just to make you understand, I have shown you certain difference. Like for example, I'll just tell you one thing. Look here. If you consider this volume change and this volume change, intentionally I have done this very slow, because actually it won't be even this much, but much small. But to make you understand, I have done this because clearly at this location the vapor phase is more. So if vapor means the gaseous phase of this liquid is more, then definitely expansion can happen. So there is some significant change in volume. But here in this region the substance is liquid, so even if you are applying high pressures, there is no much change in specific volume. That's why this line is generally very steep as compared to this line. Clear? Did you understand why this is of higher slope now? Someone is asking, Mohit. Yeah. Okay. And clearly you can understand, let's say initially if you are trying to compress an incompressible substance, practically if you go into molecular level, what happens is, initially molecules will be like this. Okay. It's not solid, it's liquid. So you have very slight packing between them. Now try to understand one thing. If these are the molecules with small gaps in between, now let's say if you are applying pressure, okay, so if you are applying pressure on this, sir, did not understand, can you again explain please? Yeah, I'm explaining. See here, 1 to 2 is compression process. Clearly you have seen 1 to 2, as your pressure increases, this specific volume will decrease, okay, because if you are clearly every fluid has certain bulk modulus. If you are increasing the pressure, then definitely volume generally decreases, okay. So increase in pressure decreases the volume. So first point is, if you are increasing this pressure from 1 to 2, which is condenser pressure to boiler pressure, then definitely specific volume at 1 should be more than specific volume at 2, because substance eventually gets compressed. Now why I have drawn a line like this is, if you take the slope here and at this point the curve is much steep, meaning in the initial phases the fluid gets subjected to some volume changes, but as you go to the top, the fluid, it is very difficult for the fluid to undergo any further compression, because initially when you apply pressure, molecules already get adjusted in this, all these molecules which are having gaps in between them, they become close. Means if you see, this volume becomes this volume and molecules inside get tightly packed. After that, even if you apply further increase in pressure, there won't be much space enough so that these molecules cannot go much closer. So that's why almost after reaching this point, even though if you are increasing pressure, there is no provision with the molecules that they can actually come close. So volume almost remains constant in this part. Clear? Because every substance has certain bulk modulus which changes with pressure and volume. Clear? That's why. Initially there is some gaps between the molecules so that they'll rearrange and the volume of the substance gets little small. But after that, the further compression, even though if you do further compression, these molecules cannot fit inside very effectively. Clear? That's what. Normally in fluids, in bulk modulus and all, if you go to detailed explanations in full course, normally I explain this, but in fast track I think I have skipped this best because of time. Now converting this to TS is the main job, main interesting job. Converting to TS. Converting to TS actually here. Okay, so converting to TS. If you convert to TS, let's see. TS and dome is important again. Okay, now let's see. If there is dome like this, then again, you know, in case of TS, in basic thermodynamics you might have seen, the line of constant pressure looks something like this. See here. This line is actually for, let's say it is for condenser pressure. P condenser, and let's say you have boiler pressure also. So boiler pressure may be something like this. You know, the lines on the left side are very close to each other. Actually, you cannot draw on a single board or single page. Like let's say for example, if I show condenser and boiler here, I cannot show condenser and pressure on the condenser and boiler on the superheated region because they will be diverging so much actually. Okay, practically you cannot show them on a single board, but anyway, for your understanding, I'm just drawing them. Now let's see, you have P boiler. Okay, so you have two pressures like this. So TS, and these are two constant pressure lines. Now let's see, if this is the initial state, then clearly this is point 1. Now process 1 to 2 is isentropic. So if the process 1 to 2 is isentropic, because you know we assume everywhere it's reversible and all, and we know the effective way to compress any substance practically is adiabatic. So if you take this process as isentropic, on TS diagram this turns out to be a straight line like this. Okay, so 1 to 2 like this. Clear? I think I can slightly increase the line thickness, no? Better? Yeah, 1 to 2 like this. So it lands on this point 1 to 2. So this is your compression. Clear? 1 to 2 is your compression. Now from 2 to this point 3, means from liquid to complete vapor, this process is completely happening along constant pressure. If this is along constant pressure, and since the line of constant pressure is like this, that means my heat addition will take place something like this. So it takes place something like this actually here. Okay, so this point is point 3. This point is point 3. So this is your heat addition, small part of heat addition, 2 to 3. Now again from 3 to 4, this expansion is isentropic up to condenser pressure. So clearly if you take a line, this is your isentropic expansion. 3 to 4, again isentropic expansion, and phase change 4 to 1 is at constant pressure. So this is 4 to 1, which is constant pressure heat rejection, or in condensation that happens in a condenser. So this is QS 4 to 1. So this is S equal to constant. Of course, you know there is heat addition in this process. There is heat addition in this process, and heat rejection is happening here. So QR, and you are getting work output. Work output here. Clear? So this is what you have. So this is W out actually here. Now this is the actual cycle which is proposed by the Rankine, but this is theoretical cycle, but it got certain corrections. First of all, tell me one thing. Out of all reversible cycles operating between same temperatures, which cycle has highest efficiency? You might have studied in second law of thermodynamics, basic thermodynamics. In second law you might have studied. Out of all reversible cycles operating between the same temperatures, which cycle has highest efficiency? All cycles have same efficiency, correct? That's what 𝐂𝐸 theorem tells now. All reversible cycles operating between same temperature limits will have equal efficiencies. Studied this statement? 𝐂𝐸 first corollary. Have you studied this? All reversible heat engines operating between same temperature limits will have equal efficiencies. Correct? This is what you have studied. Yes, no? But the condition is all those cycles should have constant temperature heat addition and constant temperature heat rejection. That's the process. Okay, it need not be 𝐂𝐸 exactly, but like when I'm talking about gas power cycles, I'll talk about Ericsson, Stirling, these cycles also. All reversible cycles which are operating between same temperature limits such that heat addition and heat rejection are at constant temperatures, then all these cycles will have equal thermal efficiencies. This is what 𝐂𝐸 corollary is. Okay, and what I asked you is actually 𝐂𝐸 cycle is correct, because in case of 𝐂𝐸 cycle, heat addition and heat rejection are actually very isothermal. Now one important point is, why did Rankine suggest this particular cycle, but why he did not suggest in some 𝐂𝐸 cycle? Because look, I might have drawn two different cycles also. Now you all understood how I have formed this TS diagram. Okay, now let's see. If you have this TS directly, okay, so T and S, and let's say I am drawing the dome like this. Now let's say I am drawing again two constant pressure lines. See carefully, guys. I wanna talk some important things here. Okay, concepts. And the actual Rankine cycle that you have, ideal Rankine cycle that you have is 1 to 2 is this process. 1 to 2. Then you have 2 to 3 heat addition. 2 to 3 is heat addition. Then 3 to 4 is this expansion, and 4 to 1 is what you have as the heat rejection. Okay, so anyway, I'm just writing the things. pH is, this is P boiler and P condenser. You know, this is the cycle that we got in ideal 𝐂𝐸 cycle. Sorry, ideal Rankine cycle. Now clearly I can ask you one thing. From your second law point, you know, thermal efficiency is equal to 1 minus TL by TM actually, correct? Sorry, TH. Okay, so TL by TH is what here, where TL is the temperature of heat rejection and TH is the temperature of heat addition. But the complete heat addition and heat rejection should happen at those two temperatures. Means this should be the temperature at every point on the heat rejection process, and this should be the temperature, TH should be the temperature at every point on the heat addition process. You know this. Now if you see this cycle 2 to 3, it is actually constant pressure process, but not isothermal process. This is isothermal, of course, because it's phase change of pure substance, but 2 to 3 is not actually isothermal. So one thing that you know here is this TL is constant in this cycle, but TH is not constant. So we define something called TH mean actually. Okay, so TH mean is called mean temperature of heat addition. Mean temperature of heat addition. Mean temperature of heat addition. So what is this mean temperature of heat addition? You all know, if the cycle has to have maximum, or basically if there is a working substance which is at some high temperature, or there is some substance actually, if you want to get a maximum work out of that substance, the heat which is supplied to that substance should be at high temperature. Means, you know, supplying 1000 kilojoules of heat at 400 degrees Celsius or 400 Kelvin and supplying 1000 kilojoules of heat at 700 Kelvin. Are these two equal? Are these two equal? In first law of thermodynamics point of view, are these two equal? Just tell me. In first law of thermodynamics point of view, means in terms of energy conservation, let us say I told you I am giving heat of 1000 kilojoules. Then is these two equal or not? Come on, type in the chat box. They are equal, correct? They are equal in case of energy conservation, because normally in all your energy conservation questions, or basically in the first law of thermodynamics, you never talk about the quality of the heat. You just talk about the quantity, and we'll just say there is 1000 kilojoules of heat which is supplied. But in second law point of view, if you see, are these two same? In second law point of view, in second law thermodynamics point of view, if you see these two heats, two amounts of heat, is these two having same capacity to generate work? Are they two having same capacity of generating work? No, correct? Because we defined something called one easy chapter again, which is 𝐂𝐬𝐧𝐤𝐬, correct? So therefore, high temperature, it has high quality. Yes, correct. Of course, we can understand. That's what we have. We'll say it has high 𝐂𝐬𝐳. So this is more powerful than this, is what we know actually. Okay. Now, if you know this, whatever we'll try to do is, all the heat whatever we are trying to supply, we will try to supply that heat at high temperature. Because of 𝐂𝐬𝐳 knowledge, we know that all the heat what you are supplying from 2 to 3 has to be supplied at high temperature. But here in this case, this process is not constant temperature process, means over some part of the cycle we are compromising on temperature of heat supply. Okay. Now clearly one thing, you know, if TH mean increases, thermal efficiency of this cycle also increases. So how do we calculate TH mean? First of all, TH mean is equal to heat supplied divided by same amount of entropy change actually. Okay. Means let's say in this process 2 to 3, if this is the entropy change which is having here, which we are having, this is delta S in this case. So if this is your delta S, then definitely this mean temperature of heat addition is that constant temperature of heat addition such that the area under this curve 2 to 3 remains same with the same change in thermal efficiency. Like I'll just explain you in maths. I think I have told you in fluid mechanics also. Normally in maths you have this theorem called mean value theorem of integration. I've told you this already, I think. Let's say if this is T2S, okay, TS, and your curve is something like this, 2 to 0.3, this is heat addition in general. And normally if you see the amount of heat added, that's nothing but this area which comes under this. This comes under this area, okay. So this complete area, this is the complete area, and clearly you all know Q223 is equal to, or Qs is equal to integral state 2 to state 3 TdS, because it's a reversible process. So you know del Q is equal to TdS. So del Qs total heat supplied is integral 2 to 3 T into change in specific entropy. Now we can define some temperature somewhere like this. Look here, somewhere like this you can define some temperature such that whatever the area you have here, the same area you can, means basically whatever the area you are losing on the top, same area you can compensate here. Of course in this diagram it's not scalable exactly, but at some point between this point and this line you can fix some line where the area under this white line is actually same as the complete yellow shaded area. So if heat transfer is same, this is also equal to mean temperature of heat addition into same delta S actually. Okay, so this implies your Tm is equal to Qs by delta S, which I have actually written here. Okay, so this is normally called mean value theorem of integration. Yes sir, area under mean line compensate the original area. Yes, exactly. Okay, so whatever the area you are losing here, same area gets compensated here. Okay, so that's what we actually take. This is normally called the mean value theorem of integration, which I think I have already told you in fluid mechanics. Okay, do you know when I have taught you in fluid mechanics? Can you remember where I have taught you this mean value theorem of integration in fluid mechanics? I have taught you at one point. Where is that? Do anyone of you remember? In fast track. Do anyone of you remember where I have taught you that? I remember from your maths lecture. Okay, fine. In fluid mechanics, I have used it somewhere. Any idea? In maths. Okay, all of you learned this in maths from me. Okay, fine. But actually, I have used it during turbulent flows. You remember, I was doing mean value of velocity. Whenever there is a fluctuation of velocity, I have defined some mean value. Okay, so they have taught you this if you remember. Clear? Now, anyway, let's see. So this is Qs. So this is actually 2 to 3 TdS divided by delta S. This is how you actually calculate this T mean. So this is integral 2 to 3 TdS divided by delta S actually. Okay, so this is mean temperature of heat addition. Now try to understand one thing here. Instead of doing this process, because in this process THM will be definitely less than this temperature, yes or no? Let's say if this temperature is TH, clearly in this process 2 to 3 THM will be definitely less than TH, correct? Because you know definitely this white line has to lie below that orange line. Now there could be two possibilities which we would have made. Look, what are the two possibilities? One possibility is this, means instead of having the cycle from 1 to 2, let's say you might have got the cycle from 1 dash to 2 dash, then 3 4 as usual. Okay, so 1 dash 2 dash 3 4 1 dash, 1 dash 2 dash 3 4 1 dash. This is actually a Carnot cycle. If you see, Carnot cycle. Clear? Because this complete heat addition 2 dash to 3 is happening at TH. So definitely, since TH is more than this TH mean, definite, and TL is locked. TL is anyhow the same thing. So efficiency might have increased actually. So this is one possibility. Or you might have also done this thing. Look, instead of stopping this at 2, you can take this up to 2 double dash. 2 double dash. Then your heat addition process is like this: 2 dash 2 double dash to 3 along constant temperature, 2 double dash to 3, and 3 to 4, again 4 to 1 as usual. So 1 2 double dash 3 4 1. So this is one more Carnot possibility. Even in this case also you might have same TL but TH along from 2 double dash to 3, the heat addition is happening at constant temperature of TH. So definitely if you compare these two efficiencies with this efficiency 3 4 1. Now if you compare thermal efficiencies here and here, of course these two are equal because both are isothermals between same temperature. Clearly you know one thing, definitely this is going to be less, correct? Because as per that formula, TL is same in all the cycles, but TH in actual ideal Rankine cycle is less as compared to this both cycles. So definitely if you would have taken one of these two cycles, definitely your efficiency would have been much better than the actual Rankine cycle. Yes or no? Can you understand this much? Instead of constructing this cycle 1 2 3 4 1, if I would have constructed 1 dash 2 dash 3 4 1 dash or 1 2 double dash 3 4 1, definitely my efficiency would be better. Yes, will you all agree with me? Because both of them are Carnot cycles with complete heat addition happening at higher temperature TH. Yes or no? Yes, it would have happened, correct? Definitely it would have been case with highest efficiency because these two guys are Carnot cycles. Okay, but these two cycles are practically not feasible. The reason is, see here, I'll tell you. The main problem is this process 1 to 2 dash. See, it is very difficult for us to stop the condenser exactly at this point, okay? Because this point will have certain Dyna's fraction of maybe 0.1 or 0.2. It is practically very difficult for us to control this state exactly, means to control this state 1 exactly at one point, at this particular point 1 dash, okay? Means, let's say for example, if the constant Dyna's fraction line, for example, x equal to 0.1 is passing through this, it is practically very difficult to exactly stop the fluid at x is equal to 0.1 and then compress it. And also you can see, normally in this location there is vapor, okay? Majority of the portion is in liquid, but still there is some significant amount of vapor. And if you try to compress the mixture of liquid plus vapor, then definitely the pump gets easily affected, okay? So that's why this process 1 dash 2 dash is not practically feasible to start your process. Clear? Which means this process 1 dash 2 dash is not fit, and also exactly stopping at 1 dash is also not possible for us. Clear? सर गेट मैकेनिकल में 50 नंबर पर कोई PSU मिल सकता है? इस साल 60 तक मिला है, आई थिंक, या मोर देन 60, इवन 58 59 तक भी मिला था, ठीक है, फाइन. But anyway, you aim for some 75 to 80 good marks. We'll see what happens after the result, okay? If I have all India first rank, I can take anything, okay? So don't think or don't limit yourself, because you still have 45 days, you can still work out, okay? Good enough, okay? Don't think of I haven't studied anything and all these things now. Just keep your preparation, and definitely this last 45 days preparation can push you a bit of definitely some good number of marks, like 10 to 15 marks easily. So you will, instead of getting 50, you may get 65 and end up below 100 also. Things can happen, okay? So see here. Fine. So did you all understand why this 1 dash 2 dash is difficult? Because practically stopping this condenser outlet at 1 dash, having certain exact Dyna's fraction is difficult, and also compressing this mixture of liquid vapor is very difficult. Okay, so that's why, because of these two difficulties, this process 1 dash 2 dash is actually eliminated. Clear? Understood? Okay. Please type in the chat box here. Did you understand this or not? Why you cannot do 1 dash 2 dash? Okay, yes or no? No? Yes? Okay, fine. So yes, okay, so 1 dash 2 dash is eliminated. Now what about this 1 2 double dash? Let's see. So this don't have any feasibility now. Okay, so fine, let's see. Okay, let us keep that for some time. So this is not possible because of condenser outlet at 1 dash, condenser outlet exactly at 1 dash, and 1 dash 2 dash compression is difficult because it is wet compression actually. Okay, so 1 dash 2 dash compression is very difficult, correct, is very difficult. So this is why you cannot do this. Now coming to 1 dash 2 double dash, I mean 1 2 double dash, actually this is 1 1 2 double dash. If you observe one thing, try to understand, these two pressures are very much different. Actually, you know, boiler pressures are, in case of even supercritical, it may go up to 20 bars and all, okay, 20 bar or maybe sometimes even 30 bars also. But P condenser will actually operate below atmospheric pressures, okay, because we have seen clearly this phase change temperature or pressure has to be much less than atmospheric conditions. So P condenser is like few kilopascals, maximum 30 to 40 kilopascals in actual case. So for pressure difference of such big range, this process 1 to 2 is actually coming here. If you think of a line which should actually pass the constant pressure process here, and it going like this, means to this particular pressure, if you want to directly compress the fluid from 1 to 2 double dash, you see this pressure ratio P1 and P2 double dash. P2 double dash is like some thousands of times of P1, yes or no? So practically using pumps, we cannot take it to that high pressures actually. Clear? Did you understand this? Compressing this pressure from, compressing this point from 1 to 2 double dash directly, which is like almost some thousands of times bigger than this P1, is not very much practically done with case of pumps. Okay, even with supercritical pumps, we are not able to generate such very high pressures actually, okay, in a single go or maybe in steps. Clear? So that's why compression from 1 to 2 double dash is also very difficult. Means practically you can see in PV diagram from 1 to 2 double dash means somewhere here going along this line means creating such big change in volume of liquid, because you know clearly this region is liquid to the left side of the dome, it is liquid. So practically bringing out such a big changes in volumes of liquids is not practically done, because you know liquids have very high bulk modulus values. Clear? So that's why practically this 1,2 double dash process is also not fit because of the compressibility issues. Okay, so this is not possible due to compressibility issues. Actually. So that's why the two possible Carnot cycles which can be done are eliminated practically, and that's why he has given a constant pressure heat addition process in case of vapor power cycles. Clear? So did you all understand this logics, why all these things are important here? Because in interviews and all, if you go to BRC, people definitely ask you this. Why you cannot generate a Carnot? Because generating Carnot will definitely give you higher efficiency, but why you are not able to generate Carnot? Many people what they do, they think of this and they'll say work done will decrease actually, okay? But then they'll ask you this case then, 1,2 double dash case they'll ask you. Then they'll ask you that 1,2 double dash case is having more area than actual Rankine cycle, so your net work output will increase actually, okay? Then why you are not going? This is what they'll twist the questions. Understood? Clear? Now, anyway, so one thing after listening to all this stuff, one thing that you are very much clear is actually, guys, sorry, I forgot to display this in the beginning. This is Rankine cycle. So these are the topics that we are going to cover today. Okay, Rankine, improving the efficiency, then reheating and regeneration. I'll put this slide somewhere where it is supposed to be there. Okay, here it is. Fine. Okay, so yes. Now let's continue our things. So anyway, this is for the mean temperature of heat addition, and we are talking about this. Okay, fine. So 1, 2 double dash, all the cycles of it. So one thing that you could understand is, moral of the story is, in vapor power cycles, heat addition and heat rejections are not isothermal, or can't be isothermal in general. I mean, heat rejection can be there, but heat addition can't be isothermal. So this is the moral of the story actually. Okay, so this has to be isothermal. Now, so clearly the ideal Rankine cycle is actually like this. Ideal Rankine cycle is something like this. If you have a T and S, temperature, specific entropy, I mean this is temperature and this is specific entropy, then you get this dome. I'm just drawing a rough sketch. By this time you might have understood the story already. So 1 to 2, so then 2 to 3 is heat addition. Okay, and this is how you have the cycle, 2 to 3, 3 to 4, correct? Sorry, this is the cycle that you have. So 1, 2, 3, 4 is the cycle. Now fine, cycle is modeled. Now you know this is going to be the practical cycle with which you are going to work out. Now definitely the ultimate thing is, one thing that you can know is, with this cycle definitely the thermal efficiency what you are going to get is less than the Carnot efficiency. Means there is some scope for improvement of efficiency. This is what you can understand. Yes or no? Practically see here, in case of, if let us suppose if this heat addition would have been isothermal, if this is only TH, then the efficiency would have been the greatest because it's nothing but the Carnot efficiency. But because of this heat addition process being constant pressure, this TH mean is actually less than TH. So that means this thermal efficiency of this Rankine cycle is actually less than the maximum possible efficiency. So we have some scope for improvement of thermal efficiencies, correct? Yes or no? So what can we do to actually improve this thermal efficiencies? That's the main thing. Okay, so Rankine cycle anyhow I was teaching for past some time. So this is Rankine cycle. Now let's see how we can actually improve this efficiencies of Rankine cycle. Okay, so let's see let's work out certain options first. A, increasing boiler pressure. Increasing boiler pressure. Okay. Now, let's say you are increasing this boiler pressure. If you increase this boiler pressure, how you know that actually thermal efficiency will increase? The reason is, see here. I'll show you with the help of TS. Temperature and specific entropy. If you have this cycle like this, then let's say I am drawing two cycles. One, 2, 3 and 4 actually. Okay, so you know 1 to 2, 2 to 3, 3 to 4 and also 4 to 1, and of course this is straight line. I think it is not looking straight, but please assume this is straight line actually. Okay, it is straight or not? Okay, again it is not straight. Fine, please forgive my drawings. Okay, I am very bad artist. 3 to 4 and 4 to 1. Okay, so this is cycle. Now let's see, you are increasing the boiler pressure. So what happens if you increase the boiler pressure? So the first thing that happens is, look, let's say if this is the line of actual boiler pressure, this is PB. Okay, so PB. Now what you are doing, you are increasing the boiler pressure to some other part. So this is PB dash. Okay, so PB dash is actually greater than PB. Okay, so PB dash is greater than PB. Now, one thing definitely you understand is, you have to take your compression up to this point, which is 2 dash. So in the new cycle, you have to take this compression from state 1 to state 2 dash. Then your heat addition is something like this. Okay, so this is your case. So this point is actually your 3 dash. Then clearly 3 dash to 4 dash, you have this, and this is how you have the cycle. Okay, so 1, 2, 3, 4, 1 is actual ideal Rankine cycle. Rankine cycle. Okay, so ideal Rankine cycle. Now 1, 2 dash, 3 dash, 4 dash, 1 is actually your modified Rankine cycle. Modified Rankine cycle. What did we modify? We have increased the boiler pressure. If you increase this boiler pressure, then how thermal efficiency is actually increasing? That's the main question, because I have kept the heading under improving efficiency of this cycle. Okay, now if you see, again if you check this thermal efficiency, 1 minus TL by TH mean is what you can say. Then observe carefully guys, in this process 2 to 3, heat is supplied along all these points, correct? Heat is supplied along all these points. In case of 2 dash 3 dash, what's happening? You are supplying heat at all these points actually. At all these points. Means if you see, the heat addition in the process 2 dash to 3 dash is happening at a higher temperature as compared to the process 2 to 3. Yes or no? Clear? At all points in the process 2 dash to 3 dash, the temperature is high as compared to the process 2 to 3. Yes or no? Yes? Clear? Then definitely if at all points of 2 dash to 3 dash, if temperature is high, then definitely what happens? What happens to this TH mean? That will increase. Okay, so TH mean in case of 2 dash 3 dash is actually more than TH mean of 2 to 3, and clearly TL is same in both the cases. So definitely for same TL is same. You can see clearly for same TL, thermal efficiency of 1, 2 dash 3 dash 4 dash 1 is definitely greater than thermal efficiency of 1, 2, 3, 4, 1. This is 100% clear. Okay, fine, done. But there are certain limits for this. Okay, you can see what are the limits. Point number 1, as I told you, your compression pressure ratio will actually increase. Okay, it is, it's practically difficult to compress liquids. Normally we use pumps. So compressing 1 to 2 is easy as compared to compressing 1 to 2 dash. Okay, so again pressure will increase. Second point, one very important point actually, if you take this line, you might have seen in basic, okay fine, in applied thermodynamics only somewhere. Look, if this is your line, if you compare Dyna's fraction at 4 and 4 dash, can anyone tell me what is the symbol between these two? What is the symbol between these two? X4 and X4 dash. Can anyone tell me? What is this symbol? Greater than or less than something? You put the symbol, type the symbol in your keyboard or phone. What happens here? X4 and X4 dash. Come on, quick. This is a phase change process, okay? So constant pressure. X4 and X4 dash. What is the symbol between these two? Come on, type quickly. Greater than, correct? So X4 is definitely greater than X4 dash. Okay, it is greater than X4 dash because X4 is greater than X4 dash, correct? Yes, because this is 0. X at this point is 0 along this liquidus curve. Along this point it is x is equal to 1, and as you go from left to right, your Dyna's fraction keeps increasing. So X4 is greater than X4 dash. In your basic thermodynamics properties of pure substances, you might have seen. Now, what is the problem with this is, clearly in case of increased boiler pressure, this 3 dash to 4 dash is lying to the left of this 3 to 4. Okay, means at all these points, if you see the Dyna's fraction, and at all these points also if you see the Dyna's fraction, the expansion along 3 dash 4 dash is having high moisture content. Yes or no? Because the Dyna's fractions at this level is actually less. At all these points of 3 dash 4 dash is definitely less than the corresponding points of 3 to 4. Now what happens when Dyna's fraction is decreasing? Means if the moisture content is increasing, the liquid particles in the gas vapor in the liquid vapor mixture keeps increasing. Okay, if liquid particles increase, what is the problem? Look, I'll tell you. Please, for what you want, please. Okay, so anyway, let's see. If this is the process, then 3 dash to 4 dash, try to understand this. If liquid particles are increasing, normally you all know density of liquid is much greater than density of vapor actually. Okay, now let's say, for example, I'm asking this. If I take some 100 grams of cotton ball, okay, and also 100 grams of steel ball, okay, and I am throwing both onto you at same velocity, which hurts you more actually? Let's say I'm taking 100 grams of cotton ball and also 100 grams of steel ball, and I am throwing at you at same velocity. Then which hurts you or which impacts you more actually? Steel or cotton? Steel or cotton? Steel ball, correct? Because hitting with steel will definitely cause higher damage. The reason is, even though both are of same mass, clearly density is more for steel. Okay, so if high density particles are hitting blades of the turbine, what happens is turbine blades will get eroded. Okay, so low Dyna's fraction in case of turbines is very dangerous. Okay, the erosion can happen at such a levels where both तेज लगेगी sir. Okay, fine. I don't want to hit you. Anyway, I'm just asking for a understanding purpose. Okay, so if I hit with this steel ball, then definitely you will get hurt more. Correct? In the same way, when high density liquid particles are coming at high velocities and hitting this turbine blades, the material of the turbine blades rips off. Okay, so the material of the turbine blades get eroded. Clear? So that's why this expansion is very dangerous. Understood? So 3 dash to 4 dash will destroy your turbine like anything. Got it? So that's why 3 dash 4 dash is a high moisture content expansion. Is a high moisture content expansion. This implies blade erosion. Blade erosion is high. Blade erosion is high. So the two practical difficulties are, this cycle definitely gives you higher efficiency as per this understanding, but because of this compression part and also because of this expansion being highly basically high moisture content, then definitely you cannot actually go for this physically. Understood? Clear? Did you all understand? Even though this is one of the way, but still why this is not very much suggestible? Yes or no? Clear? And also practically these materials have metallurgical limits. Okay, you cannot subject a particular material beyond certain pressure so that they get damaged easily. So I'm preparing for 2025. How many rank are sufficient for PSUs? Again, depends on PSU vacancies, categories, all this stuff. Okay. Anyway, I'll just repeat it. Okay. At some other point in this, because you're 2025, you have certain time. Generally, many people of our team keep on making videos about PSUs, cutoffs, and all the things. Okay. Just keep following the channel. First, sir, repeat it once. First one is this compression, no? Like normally if you see 1 to 2 is of certain pressure range, but 1 to 2 dash is of higher pressure range. Okay, means P2 by P1 is less as compared to P2 dash by P1. So this pump has to operate for certain higher pressure range actually. Okay, again pump loading cases on that. Clear? Now let's see what is the time, by the way? 5. Okay. Daily time is running up very fast. Huh? Now let's see the second option is lowering the condenser pressure. Lowering this condenser pressure. So normally condensers operate below this atmospheric pressure, but still if you low this condenser pressure, then what happens? Let's see. Let's have certain idea on this. T S, you have got your dome. Again, I'm just drawing the diagram because you know these things already. So 1, 2, then 3. Sorry, just a second. 3 and 4. So this is what you have here. Okay. So 1, 2, 2, 3, then 4, 2, 1. Now let's say this is at one particular condenser pressure initially, P condenser, and let's say you define one more pressure which is much lower than that, significantly low, PC dash. Okay, so let's say this is PC dash, so that you all know PC is more than PC dash. Actually, in basic thermodynamics you have seen that pressure decreases all. Now let's see one thing. If you expand it till 4 dash, let's see what happens. If you expand it till 4 dash, actually, if you expand it till 4 dash, and let's say you are closing the cycle like this. Okay, again please assume all these are horizontal lines. Okay, then this is the new part of heat addition. Anyway, pump work doesn't change much, so this is 1 dash. Now clearly if you take 2 cycles, 1 2 3 4 1, 1 2 3 4 dash 1 dash. Okay, so let's say these are the 2 cycles. Now in these 2 cycles, if you see, QS is same. Correct? QS is same because this process of heat addition from 2 to 3 is not changing. So QS is same. Then turbine work is getting generated by more amount because expansion from this pressure to this pressure and expansion from 3 to 4 dash, if you see 3 to 4 dash is higher pressure ratio, that means you are extracting more work from the turbine. So WT in case of 1 2 3 4 1 is definitely less than WT in case of 1 2 3 4 1 dash. I mean sorry, 4 dash 1 dash. Okay, 1 dash 2 3 4 dash 1 dash. Okay, there's a dash here also. Fine. Clearly work done in the turbine in this case is large because you are expanding the steam to from this point to much higher point actually here. Okay, so to much higher point actually. Now clearly you can understand, because QS is same, this implies thermal efficiency in case of PB is less as compared to thermal efficiency in case of PC actually. Okay, so in the case PC, and here if you see it as PC dash, then clearly you can understand thermal efficiency increases. Okay, but again it has also got certain practical problems. Okay, first of all, did you understand how thermal efficiency increases if I decrease this condenser pressure? You may ask me one doubt also, turbine work is increasing, but pump work is also increasing. Again, you can see, because initially my compression is only from 1 to 2, but now it should be from 1 dash to 2. Okay, so pump work is also increasing. You can ask me this question, pump work is also increasing, so how can you decide W net is actually increasing? Because I'll just tell you one thing, guys. In open flow devices, for open flow devices, I have told you already, work done by the devices, control volume, is equal to minus integral VdP. Okay, I told you this. Now, if you understand one thing, this pressure drop and this pressure drop both are same. Means in case of turbine, because of this condenser pressure decreasing, in case of turbine and in case of pump, the change in pressures is same. But if you see, Vf is much less than Vg. Okay, so here in this locality, the specific volume of the fluid is very less. So this value is very less, and normally the pump work required is actually very small. Okay, so normally in case of industries and all, you generally run pumps by taking electricity, like how you run in home. Okay, but in case of gas turbines, you cannot run gas compressors using normal electricity. Okay, so always some part of turbine work is actually given to the compressor work. We'll see why and all that happens. Now this is minus VdP. Now compared to the increase here, the increase here is actually very small because of this understanding. Okay, so that's why this W net will actually be more in this case, and thermal efficiency will be highest. Clear? So till this point, did you all understand how thermal efficiency increases if you decrease condenser pressure? Yes or no? Yes or no? So please type in the chat box. Clear? If you have any doubt, you can ask me. Yes? Okay. Fine. Thermodynamics is all like story, correct? In fluid mechanics, I was doing a lot of math, differential equations, nonlinear, everything. But in thermo, we are chilling out, correct? I'm just telling you some story. Fluid is coming, this line, that line, that's it. Some geometry, and just we are enjoying, right? No need of very big thermo, very big mathematical expressions and all. It's looking easy, correct? Yes or no? How many of you are feeling this thermal is easy compared to fluid? Definitely all of my students will be feeling that, right? Because in fluid I was using vector integrations, all the stuff. But here just you see small differentiations, multiplications, ratios, simple fractions, all these things, correct? How many of you are feeling this? You type me in the chat box. Sukhma is feeling easy. Yeah, a little bit easy. Look, I'm telling you, both are actually very important subjects. Okay, so one deals with direct energy interactions, and fluid mechanics normally is much concerned about mass interactions. Okay, more than mass, the effects of rotationality, all these things are very much high. If you want a look, if an airplane is flying, there's a lot of fundamental fluid mechanics that comes into picture. Okay, so everything is important, but everything ends with numericals, sir. Definitely, yeah. Guys, I'm telling you one thing. Okay, so for past 4 days I'm teaching continuously. Shall I spend 5 minutes on some general knowledge for you? Because I think you know, people are entertaining you so much, but I think I have this feedback also. I don't know very much, but Vanessa is like very content based, teaching 100% of the, using 100% of the class only for teaching content. Nothing, no ads, no entertainment, correct? Okay, I'll just tell you 5 minutes. Look, when you go for any interview, or if you go for any higher studies or interviews or work in PSUs and all, do you think when you are, let us suppose you got scientist in like I was doing previously, let's say you are scientist in BRC, okay, or maybe in DRDO or ISR or anywhere, do you expect people ask you to sit down and write definition of thermodynamics and definition of first law, second law, all these things? Do you think people do that? Do you think after giving you a job, they'll ask you to sit and write, okay, beta, so write down what is an rotational flow, right? What is first law of thermodynamics? Do you think this will happen? Never. Okay, you are not supposed to write definitions or anything. One thing that you should always do is you should mathematically analyze the things. That's the main important point. Okay, so you should always try to like looking at your definitions or looking at your physical phenomena, you should try to model into mathematical equations, and you should write, like let's say सर 23 को HPCL का एग्जाम ही, उससे लिए कुछ प्रिपरेशन नहीं किया, अपीयर करूँ या नहीं? I'll tell you about this also. Look, I'll tell you, let's say for example, there is some block which generally I use before starting differential equations. Let's say there is a container belt, for example, okay, and on this container belt, let's say some crane is dropping, there is a crane, and this crane is dropping boxes onto this container, and this block is moving, okay, with velocity v. Now if this block has to move with velocity v, then definitely you should know what should be the torque which is supplied to this rollers. Of course, this is the formula, but if you are driving these rollers with the help of some motors, depending on this velocity, you can also calculate what is the power. So depending on the power rating, you should actually order motors, okay, electric motors which drive these wheels so that your block moves. And clearly, you know, if you want to do all these calculations, one thing that you know is, I think recently I also was talking about Newton's second law, all these things. So this is a differential equation, okay. Luckily, you need not remember all the techniques and all because you have solvers and in industries, but the main point is you should know the physics, and converting of the physics to math is really the important point, okay. Let's say if I construct a nuclear reactor, for example, okay, in this nuclear reactor, because of fission, definitely temperature increases. How to control the temperature means, if this much amount of reactions are happening and in each reaction this much amount of heat is coming out, what should be my coolant, what should be my density of the coolant, what should be my thermal conductivity of the coolant, such that it can manage the temperature. All this you have to do conversions, okay. Have you ever seen the shape of nuclear reactors? Any one of you? Have anyone seen the shape of nuclear reactors? Normally, roughly, what could be the shape? What could be the shape you might have seen somewhere? In some pics or somewhere you might have seen. In some pics or somewhere you might have seen normally. No? Cylinder, spherical, correct? Let's say it is spherical, okay? You have some bowl and all, cuts like this, okay? Now, if you have spherical and if your heat is flowing out, for example, if you are catching, of course, there is a very long cladding so that it could not leak the radiation and all. So now if you see, for example, if you want to calculate a cylindrical or maybe some spherical shaped objects, and if you want to analyze how much heat is coming through the spherical shaped bowl, okay, then definitely you should know about heat conduction in spherical coordinates, and also you should know how to consider for radiation losses, okay. So radiation plus conduction in because of some spherical objects, okay. So you have to understand these things. Now tell me, if I study the value of conduction and if I am writing Fourier's law of conduction, Q is equal to minus K gradient of temperature, do you think this can directly solve the problem? You all know this now. Heat flux is proportional to temperature gradient, of course with a minus sign. Yeah, I kept minus already. Heat flux is always proportional to gradient of temperature. So let's say if you are equating, thermal conductivity comes in. Do you think this equation directly will help you in doing all the analysis? No, correct. So that's why I'm telling you, if you want to do something technically, if you say that I want to leave this technical side and go to MBA and settle and all, it's fine. But if you want to do technical stuff, definitely one thing that you all should know is maths, okay, because everywhere you have to convert your physics to maths and do certain mathematical analysis and then try to understand the solutions, okay. Means, for example, if I say, for example, after solving a differential equation, I have modeled something. After solving some differential equation, I got something like this form, K1 into e power minus K2 into T, something like this, okay. This K1 is again properties of so many things, thickness of the wall, H, U, A, all these things, okay, and K2 is some other properties. I should know at what time my temperature in the reactor will reach certain point, so that I should immediately switch on the cooling, okay. If I use Internet of Things, for example, normally the valve, normally you have sensors and actuators all along. So if you want to actuate the cooling valve, let's suppose there is a valve which is controlled from pressure, and let's say that pressure is operated by a valve which has a sensor. You should know exactly at what time you should on the valve, so that by the time temperature reaches that threshold value in the reactor, this coolant flows in unsteady state. I'm talking, okay, means if you're owning the plant, actually switching on the plant, clear. So all these things are actually very very powerful insights, okay. If you're enjoying in your home, sitting online class, watching online class with electricity and all, then definitely people in the power plant are doing all these calculations. Okay, so you should know maths. Clear? You all say na, generally yesterday also when I'm teaching, many of you are commenting, sir please teach maths, all these things, because you believe that I know maths very well, correct? The reason, and when I'm teaching technical subjects like fluid mechanics, applied thermodynamics, or heat transfer, or basic thermodynamics, sometimes you know that normally when I'm teaching, all of you having some nice opinion on me, feedback and all. The reason why you're understanding is because I'm able to explain all the mathematical logics clearly. That's why you're liking. Let's say for example, without telling these logics, or in yesterday's class we were talking about some questions where mathematical understanding is required. Let's say without explaining this, if I tell you directly, let us say if I put this and say this is the Rankine cycle, so H1, H2 and all, you do the analysis. Will you enjoy the subject? Or in future, if you want to present it somewhere, will you be confidently presenting it? Definitely not. Okay, so that's why as a teacher I always try to give my best to my students, whoever it is, doesn't matter. And also definitely I'm telling, having strong mathematical background will create so much confidence in you, and if your maths is strong, all your technical subjects becomes very easy. Pakka. Okay, that's why initial days I was teaching maths and then going from all these things. Okay, fine. No, nobody is like weak in maths. Okay, I'm telling you, if you feel that you don't know something, just spend some time, work on it. That's it. Do you think I can solve all the spherical coordinate partial differential equations straight away? No, even I cannot solve. Okay, but many of the people in the world, even who are much better than me, cannot solve. Okay, the reason is, it's like we haven't done many good number of times, or maybe it can also happen that there is no necessity in life of daily solving it. Okay, so that's why we don't go, but generally this is very much important. Clear? Okay, so fine, enough of story for 5 minutes. I started at 5:07, it's 5:12. Okay, so again maths, calculation, subtraction I have to do. Fine, so what we are doing, yeah, so this increases the thermal efficiency. Clear? Is this point clear to all of you? First of all, it increases the thermal efficiency, then we'll see what are the problems in this. Okay, fine, clear? So can you all understand how this thermal efficiency will increase actually? If it is fine, then we will see what are the problems associated practically in doing this cycle. Okay, now let us see what are the limitations. Limitations. Look, this condenser is actually operating at a pressure which is less than atmospheric pressure. Means PC is already what is the spelling of already? PC is less than PATM. Less than PATM. Further decrease in PC can cause cavitation. And there is one particular problem which is called aeration. Actually, you all might have heard this word in your schooling or somewhere, aeration. So what is this aeration? Normally if you see atmospheric air, normally in case of castings also this is a very big issue. Okay, in case of mold preparations, if somewhere, some location pressure is less than atmosphere, then definitely atmospheric air will try to enter that pores, enter that locations. Okay, so which is a very big problem, and that's called aeration. Normally we use deaerators to eliminate that problem, but anyway, right now all this deaerators, cooling towers, all this is not in the gate stuff, so just I'm not doing as of now. But if you see, this decreasing PC further can lead to cavitation, and you know cavitation is nothing but boiling of water at that particular temperature, at normal room temperature conditions, and that creates blockages in condenser tubes. Normally condensers are heat exchangers. You have it like, it's, let's say for example, if it's a shell and tube kind heat exchanger, then if you have this heat exchanger tubes, this cavitation will cause drastic damage to the tubes, and you know heat exchanger doesn't function anymore, so the condenser will get destroyed itself. So that's why this cannot be done. Also, if you see, you can again understand something here. X4 dash is less than X4. Again, Dyna's fraction will decrease, and the turbine blades, all these things gets affected. Okay, now let's see one of the third ways which we generally use. So let's see the third way, which is superheating the steam, superheating the vapor actually. Okay, so this is like superheating the vapor. So let's see what is done in case of superheating. The cycle is, as you know, TS TS. You got a dome like this, you have a dome like this, then your cycle is actually something like this, 1 to 2, then 2 to 3 you have this heat addition, and 3 to 4 is what you have this, and 4 to 1 is something like this. Okay, so I think I'm drawing very poor. Okay, fine. So let's see. Okay, so and this is gain line, so I have to extend it. Oh, sorry. Okay, so this is 4 to 1 actually here. Fine. So 4 to 1. Now let's say this is 3 and this is 4 clearly, and this is the line of constant pressure, P boiler, P condenser. Okay, so this is P boiler and also P condenser. Now in case of superheating, so what is this superheating is basically you can increase the temperature to certain point. This is 3 dash. Now from here if you do isentropic expansion to 4 dash, pressure ratio is same, no issues. So this is 4 dash and 4 dash to 1 actually here. Okay, so 4 dash to 1. Now clearly you can see superheated cycle, superheated cycle is like 1, 2, 3 dash, 4 dash, 1. Now one main advantage here is how this is giving better efficiency, because if you see thermal efficiency is equal to 1 minus TL by TH, mean this is actually called Rankine efficiency sometimes. Okay, Rankine efficiency, or normally in general terms we call it thermal efficiency. If you see, because of this extra part of heat addition 3 to 3 dash, you can see all these points are getting heat supply at a higher temperature. Yes or no? Because of this portion 3 3 dash, due to 3 3 dash, TH mean increases. Yes or no? So this is going to be increasing, correct? So if TH mean is increasing, but you can see TL is still same. Okay, so TL is actually same. So definitely for same TL, thermal efficiency increases. Okay, so this thermal efficiency will increases. Guys, please don't feel I'm teaching so much theory. All your theoretical questions which you are mugging up have answers now. Okay, with logics. Clear? Because you know, all of you know H1 minus H2, all these calculations and all. Anyway, I'll also teach after some time. That all you can do. But when things come theoretically, majority of you either try to mug up the answers and try to end up with the wrong answers in exam. Okay, so that's why that should not be there. All this theoretical explanation what I'm giving will make all your theoretical questions getting answered. Okay, very easily. Fine. Now anyway, let's see for same TL, thermal efficiency will increase. Now if thermal efficiency is increasing, one advantage here is X4 dash is actually more than X4. That means safe for turbine health. This is safe for your turbine health, because at all these points, clearly you can see at all these points, at least at all these points, the dryness fraction is much more high. Normally this X4 dash will be somewhere around 0.97 of this range in actual cases. Okay, somewhere in actual cases. In actual cases. Okay, so in actual cases this can be done. X4 dash is proportional to, I mean this is around 0.97, 0.96, 0.9 point something above 0.9 in general. Okay, 0.92 to 0.97 is what it is maintained generally. So this actually has extra advantage. The only limitation in this case is this T3 dash. You cannot go up to very large values because every material has got some metallurgical limits. Okay, apart from metallurgical limits, this cycle don't have any thermodynamic limits like we have in the previous two cases. Okay, so that's why this is the most preferred process for doing heat addition, and that's why all your cycles you see as 1, 2, 3-4-1. Understood? Now did you all understand? Therefore the Rankine cycle is modified as, the ideal Rankine cycle is modified as Rankine cycle is modified as, if you now take this TS, now I'm going to draw the diagram which you all will like, which you all are using for so much time, which is this TS, then you can see we have some bit of heat addition, 1 to 2, then along constant pressure, you know, this is your heat addition, and clearly you have your heat rejection along this line. I mean, sorry, this is work done in the turbine, so this is the expansion in the turbine. So 3 to 4 and clearly 4 to 1 is what you have. Okay, so this is your 4 to 1 process, which is your heat rejection. Okay, so this is isentropic expansion, this is again at constant pressure, and this complete heat addition is at boiler pressure, and this is isentropic. So this is the final sketch which we are using and which you generally use in all your Rankine cycles. Clear? Did you understand? Did you understand? Instead of, out of 3 possibilities we have, increasing boiler pressure or reducing condenser pressure or increasing or superheating the steam. Superheating the steam is the best possible method, and that's what we are doing, and this is the cycle which you generally see. Now let us start thermodynamic analysis. Okay, so let's see the thermodynamic analysis here. So let's see thermodynamic analysis. Thermodynamic analysis. Okay, now clearly this is a constant pressure process, so let us write 1 to 2. In this isentropic W1 to 2, if you take magnitude, this is nothing but H2 minus H1, because you know del W of the control volume is equal to dH is what we have finally. Okay, if you see this is minus dH, of course. So in from steady flow energy equation, if you neglect heat interactions, okay, kinetic energy, potential energy, all this you want me to write, okay, fine, I'll write, spend some time. So if you write del Q minus del W is equal to dKE plus dPE plus dH. Okay, now you can see this is 0 because isentropic compression. These two guys we are neglecting because compared to this enthalpies, these two are very small, so neglecting. So if you neglect, this implies minus del W is equal to dH, so del W is equal to minus dH. Now if you do the integration stuff, we get work interaction for the pump is equal to, from the state 1 to 2, so minus of H2 minus H1, this is H1 minus H2, this is pump, and clearly you know this quantity is negative because 1 is below and 2 is top, so magnitude of pump work is equal to H2 minus H1, and you know pump is a device which actually needs some work. Okay, so this is just some bit of maths. Then coming to boiler guy, okay, so 2 to 3. Now clearly boiler doesn't give any heat, any work output, so del Q minus del W is equal to dKE plus dPE plus dH. Okay, then you can see these two if you neglect again, and boilers do not produce any work output, so del Q is equal to dH. So if you integrate from 2 to 3 and 2 to 3, heat interaction in 2 to 3, which is nothing but heat addition, so Qs is equal to H3 minus H2, that's it. Okay, and practically guys, many times this Wp, because you also know from TDS equation this dH can be written as VdP. In pump, since liquids are handled, because pump is generally handled for liquids, liquids are handled, specific volume is very less, is very low, so this implies normally magnitude of pump work is very low when compared to the complete plant. So majority of the times we even eliminate this pump work. Okay, so because if you write this as integral VdP, as I told you, Normally if you take density of water 1000, specific volume is 0.001. Okay, so compared to the turbine work generated, this pump work will be very, very small. It will be just few kilowatts in actual case. Okay, so anyway, this is what you have. Then 3 to 4, again same story as that. 3 to 4, if you calculate the work interaction of turbine, this is coming out to be H3 minus H4, because same logic, isentropic, because we'll insulate the turbines, we don't want heat to lose out. Kinetic potentials, if you neglect, this is what you get, H3 minus H4. And 4 to 1 is heat loss, again at constant pressure, so we know H4 minus H1 is the magnitude of the heat ejection. H4 minus H1, this is the magnitude of the heat ejection. Okay, so these are the things that you have. Now if you want to calculate thermal efficiency, pretty much simple, you can do thermal efficiency of this cycle 1 minus QR by QS, which is 1 minus H4 minus H1 divided by H3 minus H2. That's it. Okay, and what is W net? W net is equal to WT minus WP, H3 minus H4 minus H2 minus H1. Now clearly you know, since H2 will be almost equal to H1, this implies W pump will tend to 0. So this implies W net is almost equal to work generated by the turbine. In case of pumps, guys, in case of compressors you cannot do this, okay, because in case of compressors, if you calculate integral VDP, compressors are generally dealing gas. Okay, so specific volume for gases are significant numbers, they are not negligible. Clear? So that's why in case of compressors you cannot do this, but in case of pumps you can generally neglect the pump work. If they haven't given anything you can neglect, but if they gave something you should consider. Okay, maybe this can be generally some difference of 3 kilojoules or 4 kilojoules per kg. That's what they give you, this difference, H2 minus H1 difference, but this difference will be in some hundreds of kilojoules. Okay, so compared to some 800, 900 or sometimes thousands. Okay, so this 3, 4 will be generally neglected in actual cases. Okay, clear to all of you? Okay, so everything fine? So please type in the chat box. This is just bit of maths now. Okay, all our concept building is done. Now just doing some mathematical analysis, thermodynamic analysis for thermal efficiencies and other stuff. Okay, nothing to mug up now. Right from day one, I think it's the 4th lecture, from first lecture to this lecture, did I ask you to please remember this at any time? No, no? Okay, so nothing to mug up, but you can understand everything as per the sequence. Clear? So anyway, let's see. So we have done this. Now one important question, normally it's not much important in case of Rankine cycles, I mean in vapor power cycles, but in gas power cycles it is very much important. Back work ratio. Back work ratio means basically if you compare, normally this term is very much important in case of gas power cycles, because the name itself tells you back work, because if turbine is generating power, in case of compressors, as I told you, compressors cannot be on with electricity because it's not at all economical. So some part of turbine work will be given back to the compressor. Okay, so that's why, means how much energy, how much percent of energy generated is consumed by compressor. To measure that, this is a very good quantity actually. Okay, normally this value, if it's more than 0.5 and 0.6, it's not very much, you know, perfect combination of turbine and compressor. But this value is 100% in one case. Can anyone tell me what is the, means all the work generated by the turbine will be utilized by the compressor in one case? Anyone? In one case, in case of gas power plant or gas turbine engines, I told the answer. In case of gas power plants, okay, or in case of gas turbine cycles, complete work generated by the turbine is utilized by the compressor. Where? Any idea? Yes or no? Propulsion, rocket propulsions, aircraft propulsions, jet engines, all these cases, you know, we don't need any power inside. Okay, so just it is means practically speaking, only very out of the turbine power generated, practically almost less than 1% or less than 2 to 3% generally comes into the for electrical supplies, all the auxiliaries and all, but majority is given to the compressor again. Clear? So anyway, we'll talk about that in some separate context, maybe in ESC syllabus if Vinod sir or me teaching ATD, we'll try to use that. Okay, shaft is also connected to compressor, correct. Okay, so anyway, I'll show you that construction when I'm talking about gas turbine engines. But anyway, right now if you just want to write this ratio, back work ratio is work given to the pump by work produced by the turbine actually. Okay, so that ratio means out of the generated how much is given back, that's what this ratio. And in case of pumps, you can also write or magnitude of work given to compressors by turbines. In case of pumps, this back work ratio is almost 0. This is what BWR is actually. Okay, so this back work ratio is almost 0 because since work input to the pump is much less as compared to the work generated by the turbine. Okay, normally if you calculate values comes out to be 0.02 of that range. Okay, but in case of compressors this has certain significant values, like depending on the type of engines and all we are dealing. In case of some engines it's like, in case of aircraft engines or jet engines it's like almost 1. Okay, but normally in case of power plants and all it is like 0.35, 0.4, things like that. Okay, some 35% of the work is utilized by the compressor actually. Okay, so anyway, one thing which decides the size of the boiler, size of boiler. Now who decides this? Who decides what should be the size of the boiler? Means boiler should be big or small. Who decides that? There is one very important thing which is called specific steam consumption. Specific steam consumption. Specific steam consumption. Normally it's also called sometimes SSC. Okay, so specific steam consumption. So what is this specific steam consumption? You know, specific, it tells you means something per unit. Okay, like if it is specific volume per unit mass. So whenever I'm talking about the word specific, that means something for producing 1 unit of something. Okay, now if you see, this is the amount of steam required for producing 1 unit of power, net power. Okay, 1 unit of net power, 1 unit of net power. Okay, so this means what mass of steam has to flow in the circuit. Circuit is basically this one. Okay, so normally these are called circuits. Actually this diagram is called circuit. So in the cycle, so what should be the mass flow rate in the cycle so that it will generate exactly 1 unit of power. You all know what is 1 unit of power. Normally what power is measured in these units. So 1 unit of power, normally you see a unit cost is 5 rupees, 10 rupees. So 1 unit of power is nothing but 1 kilowatt hour actually. Okay, so 1 kilojoule per second, 3600 seconds. So this is 3600 kilojoules of energy is being utilized by you. That's what we mean 1 unit of power actually. Okay, so normally if you watch your meter readings and all, 1 unit of power means basically how many kilowatt hours of power is what they'll calculate. Okay, and this is normally having some, depending on locations, we have 6 rupees, 7 rupees and all. Normally how your power bill is done is calculated based on this. Okay, now which means what should be this m dot s to generate this much amount of energy. That's what we mean actually. Okay, so m dot s is actually measured in terms of kg per kilowatt hour, is measured in kg per kilowatt hour actually. Okay, now clearly you know power generated, total power generated is equal to power generated is equal to how much is this, m dot s into w net actually here. Okay, so if I want this to be 1 kilowatt hour, what should be my m dot s actually. Okay, so this is what we need. Okay, so power generated has to be 1 unit power actually. Okay, so if you simplify this relation, finally you can end up this calculation of m dot s, means if you convert this into 3600 kilojoules, all these things, just a basic calculation if you do, you will end up with m dot s is equal to 3600. This 3600 basically comes from converting this to seconds by w net, and once you convert this into kilojoules and all and putting this w net here, upon simplification you will get this units which is kg per kilowatt hour. Okay, so I'm just giving you some homework, so please try this. It's a simple calculation. Okay, very simple calculation. So because you all need to know is how to calculate this units. That's it. Okay, so this kilowatt hour is on one side, and also this m dot s and w net is on the other side. So just simplify this as 3600 seconds and kilowatt second, and this is kilojoule per kg. So after a bit of rearranging, you will get this particular units for m dot s, kg per kilowatt hour. So this is how you calculate m dot s. And in case of vapor power cycles, if pump work is not given, if magnitude of pump work is 0, then this implies W net will tend to work input of the turbine, work output of the turbine. So m dot s is equal to 3600 by WT kgs per kilowatt hour. Guys, I'm telling all these formulas are valid generally only when pump work is neglected. If they give you pump work like 3 kilojoule per kg, 4 kilojoule per kg, something like that, you should definitely consider pump work. Okay, that's why I'm writing if. So please make this, don't mug up these formulas and all, just try to understand the things. Okay, clear? Yes or no? Fine. Okay, so this is what you have, m dot s. This is the specific steam consumption. Now if m dot s has to be large, okay, means if the amount of steam required for generating this power is large, that means the amount of vapor that the boiler has to produce is definitely large, means the boiler size is big. Okay, so this specific steam consumption is indirectly a measure of size of the boiler. If this value is large, then definitely you can write this as SSC is equal to better this because we have already taken 1 unit all these things. So SSC, specific steam consumption, is equal to this value actually. Okay, specific steam consumption is equal to 3600 kilojoule per kilowatt hour. Okay, it's not directly m dot s, you can write SSC because we have already kept 1 here. So SSC is what you can keep. Okay, so that's what we can keep because we have already told it's 1 unit. Okay, by putting 1 on this left hand side. Now this is done. Then so basically this SSC is measure of size of the boiler, size of the boiler actually. So this is measure of size of the boiler. As SSC increases, this implies you need a bigger boiler. Boiler size increases. Okay, so boiler size will become big in that case, clearly, because it has to produce high amount of steam. So for producing high amount of steam, you definitely need a big boiler actually. Clear? So these are some different things for calculating thermal efficiency. Sorry, for calculating, where is this? This now we should put one box here. So for putting thermal efficiency, then calculating W net, then back work ratio, specific steam consumption. So these are the things that you have in general. Clear? So this is basically the if questions comes from basic Rankine cycle, questions comes out in one of these places. Okay, shall we solve some 1-2 questions because I have put some questions today. So let's see. Come on, let us solve this question. A Carnot cycle works on steam between the pressure limits of 7 megapascals and 7 kilopascals. The thermal efficiency of the cycle is dash, round off to 2 decimals. At 7 megapascals, HF, HG, SG, SF is given. At 7 kilopascals also these things are given. I am starting a poll, so just work it out and round off to 2 decimal places. You enter in integer. Okay, so enter the nearest integer value. Clear? I'm giving some 120 seconds of time. Come on, start. You in poll you enter the answer, means in you know how to enter the poll, just enter in the chat box. So this poll, enter the answer in integer. Let's suppose you are getting 58.78, 58.74, something like that. Then round it off to 59. Okay, that's it. Come on, do this. You have the question, you have the diagram. Of course, diagram is not needed, I think, because Carnot is given anyhow. Theoretical calculation. Come on, do it. I hope you are entering some answers meanwhile. Okay, you're able to do that? Fine. So let's try to solve this question and then let us answer. First, we need thermal efficiency, correct? Now clearly these two are isentropics. So 1 minus H1 minus H4 divided by H2 minus H3. Okay, because 1 to 3, 4 can be in any cycle, but this is what you need. 1 minus 4 is this amount of heat ejection and 2 to 3 is this. Okay, now let's see. I think 2 minutes is not sufficient to solve this question, but it's okay. Okay, we'll solve in here. I just want you to think before doing calculations and all. Okay, so H1 minus H4. Now clearly this H1 is known to you. I mean H2 and H3 are known to you because they are nothing but Hg and Hf values at 7 megapascals. Okay, now how to calculate H1 and H4? Can I say H1 is equal to Hf at 7 kilopascals plus Dyna's fraction at 1 into Hfg at 7 kilopascals. At 7 kilopascals. This is what you want, correct? So x1 into this value. Similarly, H4 is equal to Hf at 7 kilopascals plus x4 into Hfg at 7 kilopascals actually here. Okay, so this is what we have. Now if you want H1 minus H4, because 2 and 3 values are known anyhow, so this implies H1 minus H4 is equal to, these two terms gets cancelled out. If you do subtraction, then clearly if you do a subtraction here, these two guys gets cancelled. X1 minus X4 times Hfg at 7 kilopascals. Okay, I hope you know how to write this. Okay, so if there is some point in this region, Hf plus X into Hfg, I think in basic thermodynamics you might have seen. You all know how it happens, correct? Just apply TdS equation along constant pressure, you will get it. Okay, so now if you see x1 minus x4 into Hfg at 7 kilopascals. Now x1 and x4, how to get these values? Now clearly this process 2 to 1 and 3 to 4 to 3 are isentropics. You can know S1 is equal to S2. So what about S1? Sf at 7 kilopascals plus x1 into Sfg at 7 kilopascals. Sfg at 7 kilopascals. So this is equal to S2 and Sf also S4 or S3 is equal to S4. So this implies, so if S3 is equal to S4, then S3 is or S4 is equal to S3. Let us say it would be easy for us. At 7 kilopascals plus x4 times Sfg at 7 kilopascals is equal to S3 actually. Okay, now again if you subtract these two, x1 minus x4 times Sfg at 7 kilopascals is equal to S2 minus S3. So therefore this x1 minus x4 can be written easily now. Okay, so therefore this implies this is H4 not F. Okay, so this is 4, H1 minus H4. Now this implies H1 minus H4 is equal to clearly x1 minus x4. So what is x1 minus x4 from this? S2 minus S3 divided by Sfg at 7 kilopascals. So this value is x1 minus x4 into this Hfg at 7 kilopascals. At 7 kilopascals. Clear? So this gives you H1 minus H4 is equal to S2 minus S3. So what is 2? 2 is nothing but the saturated vapor condition at 7 megapascals. So at 7 megapascals, saturated condition at vapor 5.8133. So 5.8133 minus, okay, so this is 5.8133 minus S3. Okay, so you know this is actually S at third state. So at third state this is nothing but saturated liquid at 7 megapascals. So saturated liquid property is 3.1211 divided by SFG at 7 kilopascals. So at 7 kilopascals, this is SG and this is SF. So SFG, SG minus SF, 8.2801 minus this value SF, 0.5564, 0.5564. Now this guy multiplied with HFG at 7 kilopascals. So at 7 kilopascals, HFG, HG minus HF, 2572.14, 2572.14 minus 2572.14 minus, now what is this value? HF, 162.60, 162.60, that's it. Okay, so this gives you H1 minus H4 and you will get this answer in kilojoule per kg clearly. So therefore thermal efficiency is equal to 1 minus H1 minus H4 by H2 minus H3. So you can see this H2 minus H3. Now 1 minus, let us see what is this value. You will get some value divided by H2 minus H3. So what is 2 and 3? 2 minus 3 is nothing but HFG. So 2772.1, 2772.1 minus this value is 1267. So 1267 actually. Okay, so this is 1267. So this gives you the answer in percentage. That's it. Get this value, put it here, simplify this, that's your answer. Okay, so let's check that. 5.8133, 5.8133 minus 3.1211, 3.1211. Okay, so this value divided with 8.2801, 8.2801 minus 8.2801 minus 0.5564, 0.5564. So this total value multiplied with 2572.14 minus 162.60, 162.60. So 839.87. How much it is? 839.87, 839.87. So if you put it here, 839.87. So this divided with, this value divided with 2772.1, 2772.1 minus 1267, 1267 actually. Okay, so this is the value. Subtract it from 1. This is going to be 0.4419, 0.4419 actually here, which is 44.19% is what I'm getting. Correct? Is that what you all are getting? 44.19%. Yes. So let's see if you have 44. Someone have typed 44 in this. I think none of you, because time is actually a bit short. But just I want you to think. Yes. Okay. Fine. Fine. I understand. Because time is actually a bit short for this question. What I have given you. Yeah. 44.19 is the correct answer. Okay. Because this question is actually slightly lengthy, because these two are actually isentropics and entropy at both the states is not known. Normally in actual cases, only at state 1 you won't be knowing. Okay. Like for example, if you take the diagram like this, sorry, like this, you know this, you also will be knowing this, because S1 and S2, this value of S2 can be taken as SF at this value, and S3 will be superheated condition, it will be given. Only 4 you have to identify in actual cases. Okay. Now, so this is how you actually solve the questions. Now one thing, clearly this cycle can still be made better by increasing its thermal efficiency. Okay. So one such possibility is like reheating. Okay, maybe I'll cover reheating today and regeneration in the tomorrow's class. So after covering regeneration, then we'll solve some problems and start gas power cycles in the next lecture. Okay, but we will see this concept of reheating now. So one thing that we can do in reheating is actually look how we actually do that. TS, I'm showing TS actually directly here. Let me increase this size. TS. Now you got a vapor dome like this. Okay, then you know you have two pressures clearly. Sorry, this is P condenser. This is P boiler. Okay, so practically what we are doing is actually you are doing the heat supply from 1 to 2, state 1 to state 2 actually, Then we are doing this heat addition along this constant boiler pressure, and you are doing superheating up to some point. Okay, so this is 3, and you are trying to expand in the turbine. So you are trying to expand in the turbine actually here. When you are trying to expand in the turbine, 3 to 4, let's say this point is 4. One thing you can understand is, sir, just a minute, sorry Vivek, you have some doubt. So what you said for ideal, S2 can be taken as H2. No, it's not H2. Look, I understand. In your thermodynamics you might have seen basic thermodynamics. If you have the graph like this, now for some saturated liquid actually, okay, so this is saturated liquid for example. Then if these properties are SF, HF, all these things, normally in general, you anywhere here on this line you can assume the properties at this location to be same as this. Of course they are not exactly same, but the error what you will get will be very small. Understood? Clear? Normally if you want to show, you can show calculations that if this is 1 and if this is 2, H1 minus H2 is equal to specific heat at constant pressure Cp, and of course for liquids we have only one specific heat, C into T1 minus T2, like this. But compared to this values, this value will be practically very small, because if you take this as 4.18 and let's say the temperature difference is some 20 degrees Celsius, okay, then clearly this is only 80 kilojoules, but in fact this H1 and all will be some very large number of kilojoules actually. Okay, so that's why. But anyway, it's if calculations are not given then you can assume, but if calculations are given then you can calculate accordingly. Fine. Now what I'm going to tell you is, see here, if you are expanding this steam 3 to 4, if you compare once it starts entering the dome, okay, so at this point if it starts entering the dome, the amount of or the capability of steam to do work decreases, because as the steam expands from here, liquid content keeps increasing and further expansion cannot happen. Okay, means once it starts entering this dome, then definitely at that point, till this point it is completely vapor, but once it starts entering the dome, liquid particles keep generating in the steam, and the capability of expanding of liquid particles and generating work will actually decrease very much. Okay, so that's why. But the steam here is still hot. Okay, you have very hot, means if you allow it to expand, you will have very hot liquid. Okay, so with the help of liquid you cannot do much amount of work, but at the same time this is at higher temperature. So what we will do is, generally we will actually at this particular point, see, understand the techniques here. Okay, so if this is the point here actually, okay, so this is 0.4 and you have one more pressure in between these two, this is P intermediate, some intermediate pressure, you have this intermediate pressure like this. Just a minute guys, sorry. Because I should be very careful when I'm doing this. Okay, I'll tell you the reason why. So let's say this is P intermediate. Okay, so if this is P intermediate, fine. Okay, let's see. If this is P intermediate, then what you will do, taking the steam from this temperature to again this temperature is relatively easy here. Okay, so reheating means heating once again. So we will go to this state 5 actually, because taking steam from this temperature to T3 is difficult, but taking this vapor from T4 to T5 is easy comparatively. Okay, so that's why this part of reheating is actually easy as compared to 2 to 3, because anyhow if you keep expanding here, work generated will not be much actually. Okay, because already liquid particles start coming into the picture. So at this point, instead of getting that small amount of work, you will actually raise this to some other temperature. I mean, in actual case of reheating, perfect reheating, T3 and T5 are made same. So you will now expand this into the turbine. Okay, so this is how you have the turbine clearly. Okay, so this is the turbine. Clear? So this point which is here is your 0.6, and this is second stage expansion, and of course you have the closing in the condenser. Okay, so you have this condenser, closing condenser. So this is actually your 6 to 1. Now clearly you can understand the technique here is, instead of getting this small amount of work, since it is much easy to increase the temperature from 4 to 5 as compared to 2 to 3, so therefore you will do once again heating of the steam. So that's why it's called reheating, means reheat. You'll do it, you heat it once again, that's what. Okay, so you will do reheating, and comparatively in this portion specific volume will be large as compared to this portion. Okay, so that's why, because in this portion it's almost inside the dome, so definitely it's like having less specific volume because of vapor content. But compared to here in this locality, the specific volume here will be low, so definitely here you will be getting more work, means this H5 minus H6 will be large as compared to H4 minus, let's say for example if it have expanded something like this to 5, compared to this work will be definitely more. Okay, so because of higher specific volume between the same pressure. Okay, because the pressure difference between these two and these two is same. Okay, but the specific volume in this domain is actually large. Clear to all of you? So this is your state 4 actually. Did you all understand this? Can you all understand one thing? If I would have expanded this 4 to 5 somewhere here, the work what I would have got will be definitely less than this work, because the pressure ratio between this 5 to 6 and this 4 to maybe this point, if I call it 7, the pressure ratio between 5 to 6 and 4 to 7 is same, because these two are lines of constant pressure. But compared to this locality, in this region specific volume is high, so definitely you will get higher work. Okay, it will not end exactly on vapor line. Theoretically it should end here, but practically it won't end. Okay, because of some heat loss and all, definitely things get eliminated. So specific volume did not understand. I'll tell you. If you take liquid, I mean if you take any system, any liquid in general, like if you start heating, if you take specific volume at this point and at this point, at which point, means if I call this point A and if I call this point B, at which point specific volume will be high? At which point specific volume will be high actually? At which point specific volume will be high? Point A and point B. You're expanding, okay, and system got completely converted to vapor, correct? You know, at B it is having higher specific volume. Okay, because see, it is just vapor here. If you keep on heating vapor, then specific volume gets increases. Okay, so that's why specific volume at B is much high as compared to B. So that's why, because of that, expansion in this stage would have given less amount of work as compared to expansion here 5 to 6. So that's why by use of this reheating you can actually get extra amount of work, okay, in 5 to 6. So clearly one thing that you know is, normally this two reheating stages, we have two turbines in this. 3 to 4 is expansion in high pressure turbine. Expansion in 3 to 4 is expansion in high pressure turbine. In high pressure turbine, and 4 to 5 is like expansion in low stage, expansion in low pressure turbine. Normally if you draw a block diagram, low pressure turbine. Okay, so normally if you want to construct a block diagram, I'll see, just you have a boiler plus superheater. Of course we generally know now it's not only just boiling, superheating also is there. So superheater. So if you have this, what happens here is you have two turbines. One is the high pressure turbine, okay, and second one is the low pressure turbine. Clear? You also have the low pressure turbine. How do you decide which is low pressure and which is high pressure? Is definitely depending on their operating ranges. Okay, so since clearly sub 0.6 will be inside dome, yes, 0.6 has to be inside dome. Why, I'll tell you just a minute. Okay, 0.6 has to be inside dome and the dynamics fraction will increase. Now anyway, what I'm telling, how do you decide which is high pressure turbine and which is low pressure turbine? Because if you see these 2 points, inlet, just a minute, something happening. Okay, fine. So if you take this point which is entry to one turbine, like you can see, if I nomenclate them, you can see, I'm just trying to put a small sketch here. just this is the block diagram, okay? High pressure turbine, low pressure turbine. Clear? So this is your condenser. And you guys get a pump here, okay? So now if you want to mark the states here, okay, so we can just mark the states 1, 2, 3, 4, 5 and 6, which is same into the condenser like this, okay? So this is how you have the construction, typical construction. Now how we decide that this out of these two turbines, so this expansion 3 to 4 is happening in one turbine and 5 to 6 is happening in one turbine, because you can clearly see if you take the entry of fluid into these two turbines, definitely P3 is greater than P5, yes or no? Because this is the actual boiler pressure, this is some intermediate pressure, okay? So this curve 4 to 5 is along some intermediate pressure, so definitely compared to the pressure range, I mean if you compare P3 to P4 and P5 to P6, then definitely 3 to 4 is higher at a higher pressure range. So definitely this turbine which is operating at higher pressure range is called high pressure turbine actually, okay? Just 5 more minutes, I'll close this, then we can move forward, okay? So you can understand in case of this 3 to 4, definitely the pressure ratio on which the temperature, the pressure ratio in which the turbine is operating is actually large, okay? So that's why this is called the high pressure turbine and this is called the low pressure turbine. Clear how to identify HPT and LPTs? Clear? Okay, so fine, please type in the chat box, did you all understand how to identify high pressure turbines and low pressure turbines? Okay, depending on the pressure range which they are operating. Okay, fine. Now let's see if you want to thermodynamically analyze this cycle, okay? So first of all, this will definitely increase thermal efficiency. Reason, you can see, see, I'll tell you. First, if you want to calculate thermal efficiency here, in this case, thermal efficiency is equal to 1 minus QR by QS, which is equal to 1 minus heat is getting ejected only in this portion. So you can see clearly heat ejection is taking place in this QR. Heat addition is happening here, QS1, and also in this process, which is QS2, because 4 to 5 is again reheating. If this is 4, this is also 4, okay? So 4 to 5 is again undergoing some reheating. So H6 minus H1. So this is what you have divided by. Now heat supplied in first case 2 to 3. So H3 minus H2, because along constant pressures, you know, enthalpy difference is the heat supplied, plus along 4 to 5 H5 minus H4. H5 minus H4 is what you have, okay? So this is the expression for calculation of डायग्राम एक बार फिर से समझ दीजिए, या डेफिनेटली अंकित देखिए. सो पहले हम क्या करते हैं, यहाँ टर्बाइन, दिस इज अ हाई प्रेशर टर्बाइन. सो once you reach this point, you are again reheating, correct? So after expansion from this turbine, what you are doing, you are taking this steam again into one more heater, and then see this 4 to 5 is nothing but heating the steam again in this reheater. 4 to 5 is happening of this heat in this reheater. Then 5 to 6 you are expanding in the turbine. 5 to 6 is again expanding in the turbine. That's it. So this is the combination which we are modifying. Okay, understood? Clear? 4 to 5 is actually this reheating. Okay, so and we are definitely like boiler, this is also at some constant pressure, so we are doing reheating along this intermediate pressure line. Okay, now this is how we have the expression for thermal efficiencies, and also W net is equal to work generated in high pressure turbine plus work generated in low pressure turbine minus work magnitude of work of the pump. Okay, so what is this? Of course, all these quantities I'm writing in specific, you have to multiply with mass flow rate of steam. Now, if you see this high pressure turbine, so high pressure expansion is happening from 3 to 4. So H3 minus H4 plus. In low pressure turbine, expansion is happening from 5 to 6. So H5 to H6, H5 minus H6 minus magnitude of pump work. So pump is doing from 1 to 2, because this compression is 1 to 2. So H2 minus H1. So this is how you can calculate W net actually here. So again, once you get W net, you can calculate SSC, all this stuff. But one thing you can clearly understand, advantages or effects of reheating. Now let's see all these points. Some of you might be mugging up for past few days. So let's try to have some understanding now. Effects of reheating. So first point, what happens to W net? Look, let us suppose if I have not reheated, my expansion would be from 4 to this point. But because of this reheating, what's happening to my work output? Can anyone tell me? Because pump work is nothing changing, okay? You do reheating or you don't do, this pump is operating between same conditions, okay? If pump work is not changing, the same pressure ratio, because of reheating, what's happening to turbine work? Look, if you don't do reheating, then definitely this part is less actually, okay? Means if you have expanded directly like this, that work would have been less as compared to this, okay, which we have explained previously. So can anyone tell me what happens in this case? W net, because of reheating, net work output of the cycle is increasing or decreasing? It will increase, correct? So this is increasing. So this increases. What about thermal, heat supplied? Heat supplied in this cycle because of reheating. I want you to tell these properties, okay? How these things are changing. I want you to tell, because you know, you need not mug up, you can understand now completely. So what is happening to QS? Heat addition. Initially, if there is no reheating, only this would have been your heat addition 2 to 3. But because of reheating, again you are heating one more time 4 to 5. So definitely this reheating will be increases. I want to know one thing. Specific steam consumption. What about SSC? SSC is equal to, you all know, 3600 by W net. Clearly, if turbine work is increasing, that means power generation is increasing for the same amount of mass, correct? Yes or no? That means what happens to SSC? Please tell me as per this. What happens to SSC? Specific steam consumption. Come on guys, quick. I'll just take 5 more minutes. We'll fill this properties and we will close, okay? But SSC will decrease, correct? So SSC decreases. Fine. 4. Dryness fraction at turbine outlet. Dryness fraction at turbine outlet. See what happens. If I have not reheated, this point would have ended here, okay? So if this point would have ended somewhere here, then definitely dryness fraction would have been less, correct? So what happens to the dryness fraction at the exit of the turbine? It increases, correct? So this value will increases. Okay, so fine. One very important point. What happens to thermal efficiency? Because these two are increasing. This is also increasing, this is also increasing. So what happens to thermal efficiency? Come on. What do you think? Both are increasing, no? W net is increasing and QS is also increasing. So what do you think thermal efficiency? What do you think will happen to thermal efficiency? Sukma, you feel decreases? It will increase. Because why? That's the question. Because okay, understood? Because this part of heat addition, normally this point will be at, you may see in diagram it is actually higher than T2, but actually in actual case this will be very hot steam as compared to water, okay? Because normally water comes at room conditions here and pump do not change much the temperature of water, okay? So T1 and T2, there won't be much difference actually, very small difference will be there. But this 4 and 2 will be very different because this is very hot steam, okay? So this is hot steam, but this is just like normal atmospheric condition or slightly 2-3 degrees higher. So T4 will be much larger. So if T4 is large, this part of heat addition in 4 to 5 is happening at very high temperature. Understood? So since heat addition in 4 to 5 happens at high temperature, Clear? Normally industries report doing one reheating, mean line shift upwards. Yes, mean line temperature of heat addition will shift upward because 4 to 5 process is happening at a higher temperature. Normally industries report for one reheating, for the first time reheating, the efficiency of the plant increases around 4 to 5%. Okay, so that's what you have. But you generally don't go for 2 reheatings and 3 reheatings and so on. Normally doing multiple reheatings will again cause decrease in efficiency. The reason is, okay, I have to again plot the graph and all. We'll see in tomorrow's class because I have already extended the time. We'll see. Normally I'll just give you a hint. If your cycle is like this, if these reheatings are increasing like this, okay, so let's say if these reheatings are increasing, one thing that happens is, see here, normally the dome will be something like this. Okay, now if the dome is something like this, this temperature or this point, if you say this is TH, corresponding to this point, what happens? The pressure decrease, means you can see, I can just show you like this. You can understand, as you go forward, this pressure line and the pressure line at which you are reheating, these two lines becomes very close to each other. Understood? I'm just repeating. See here, if this is the actual pressure line at which you are, for example, doing this, and if you take this line of reheating, these two lines will be very much close to each other. That means the pressure difference across the turbine is very small. Okay, so that means power generated by the turbine because of that excess reheating is much small. Understood? So practically that will not serve the purpose of putting a turbine. Okay, so it's not at all economical, so that's why they won't do that. Normally we generally go for only one stage reheating. Clear? And that generally definitely increases this thermal efficiency. Clear? I know many of you might be mugging up these points previously, but not at all a need. Clear? And what happens to back work ratio? That also can be talked sometimes. 6th point, back work ratio. Can anyone tell me it increases or decreases? Back work ratio is pump work divided by turbine work. Okay, so pump work, nothing is changing, but what about turbine work? It is increasing. Okay, so WP by WT, WP is fixed but WT is increasing very much, so definitely this will decrease. Okay, clear? Decreases, as you know. Now you see all these points are very much easily understandable to you. Okay, nothing to mug up anything. Simple. Based on the knowledge of numerator and denominator in a fraction, you are able to decide all these things. Okay, so no need of remembering anything and all. You might have understood it. Why I'm not going for multiple reheats? Because as reheats increases, the pressure difference across the turbine keeps decreasing, and after some reheatings, it not at all matches the turbine cost and the excess power you are generating. Okay, so that's why we generally do only one reheating. Fine, we'll end up the session. So just we'll have a quick review of what we have studied today. Then anyway, let's see. We have talked about our Rankine cycle. So this is the actual construction of Rankine cycle. Now to keep this cycle better, I have explained you why you cannot canonize this cycle like this actually. Then this is the ideal Rankine cycle. So to increase this, first of all, how you know? Because since this TH mean is less than TH, you know there is some provision to improve the efficiency. So we have seen factors for improving efficiency: increasing boiler pressure, but practically this fails because of these logics. Then decreasing condenser pressure, that also fails because of these understandings. Then superheating the step vapor, this is very better because except from metallurgical limit, it don't offer any thermodynamic limit. Okay, so you can use this. So once we start this cycle, and if you do mathematical analysis of this, you found thermal efficiency, this specific steam consumption, back work ratio, these things, basic things. Then specific steam consumption we have seen. You please work it out. Okay, this is very much easy to work out. Just play with the units, you will get this. Okay, then concept of reheating. So we have seen to further increase the efficiency, to increase this turbine work output, what we can do. So we have done the reheating actually. So this is the physical setup and a bit of understanding here. Okay, so these are the things which we have done. We have solved one problem also today, one simple problem. But anyway, I still have 2-3 more problems. You please try out them. See, in this question, in a Rankine cycle due to increase in boiler pressure, what happens? Normally these kind of theoretical questions people mug up, okay, and they'll try to end up with wrong answers in exam. But anyway, if you see, in a Rankine cycle due to increase in boiler pressure, pump work decreases. No, pump work actually increases, correct? So quality at turbine exit increases. No, this will decrease actually. That's are the two drawbacks we have seen. Load on condenser decreases. Yes, this is correct. Thermal efficiency remains the same. No, thermal efficiency will actually increase, correct? Increasing boiler pressure will actually increase thermal efficiency. This is the correct answer, because load on the condenser means heat removal. The amount of heat to be removed from the steam is done by condenser. So load on the condenser will decrease because state will be much close to the previous case. Okay, means if you see this diagram, I can tell you increasing the boiler pressure. Where it is? Yeah, here. H4 minus H1 is actually bigger than H4 dash minus H1. Okay, this 4 dash is close to this H1 than 4. Okay, so definitely the amount of load on the condenser, or basically the amount of heat to be taken out from the steam by the condenser will decrease. Okay, so that's how load on the condenser will decrease in this case. Clearly you can see this 4 dash will end up close to 1. Okay, so that's all simple things. So all these kind of questions now have technical answers with you. Okay, with logics. Clear? Now you need not mug up anything in this question. By looking at this, you know answer is C. Nothing to mug up. Okay, because you practically know what happens in a Rankine cycle when you increase the boiler pressure. Okay, so there are a few more questions, some 2-3 more questions. You please try out. They are simple questions. So in today's class, what we have done is of the story is like we have seen Rankine cycle constructions. We have seen ways to increase thermal efficiency. Then we have also seen concept of, we have seen certain basic parameters like thermal efficiency, then back work ratio, SSC, all these things, W net, all these things actually. Then we have seen reheating, concept of reheating actually. Okay, so there is one more concept which is left in this, which is regeneration, which we will see in tomorrow's class. Okay, so if you wish to meet, then you can join this actually. Whoever is interested, they can just join this group. Normally discussions, technical discussions happen in a way. If people have some doubts, they pose it here. You can have a chance to get this. Okay, so only concept of reheating also I thought of finishing today, but I think it's okay. We'll do it tomorrow, and then we'll start Breton cycle. Okay, I mean the gas power cycles. Maybe tomorrow we'll start Breton along with Ericsson and Stirling cycles. Okay, because Carnot you might have already seen in basic thermodynamics. You have seen Stirling and Ericsson also in basic thermodynamics. If you have seen, I won't discuss. Let us save some time. Why doing the same thing again and again? You all have seen Ericsson and Stirling cycles, constructions like regenerators, how they act, all this stuff. In basic thermodynamics, because I am pretty much sure you might have seen Carnot, Ericsson and Stirling. Please teach. Okay, fine. I'll teach. Okay. Yeah, it's okay, fine. Okay, so I hope you got enough idea on this what we are talking, Rankine cycles. So that will be better. Okay. Any questions? Quick questions? I think things are fine because we have extended the class already 20 minutes. Are you all understanding, guys? Each and every point what we are telling? Because thermodynamics is basically like story. Okay, with a little maths, multiplications, divisions, fractions, all these things. Not to worry as much as fluid mechanics. Okay. Clear? Understandable? Okay, some love symbols are going there, so I think things are happy. Fine. Okay, so we'll meet tomorrow at 4 p.m. Okay, so we'll meet at 4 p.m. and we'll do regeneration and we'll go for gas power cycles. Okay, fine then. Thank you all. No more doubts. Okay, take care. Bye. Okay, if there's something, you can always come into that group and you can talk. Fine. Thank you. Bye.